Welcome to Dr. Hugh MacIsaac lecture. Dr. Hugh MacIsaac is from Great Lakes Institute for Environmental Research, University of Windsor. I know him for a long time. He joined University of Windsor as assistant professor in 1992, and he became a full professor in 2000. He served as a fisheries oceans invasive species chair, research chair from 2002 until 2011. And then he also served as a director for Canadian Aquatic Invasive Species Network from 2006 to 2011. Then he became like NSERC, Canadian Aquatic Invasive Species Network chair from 2011 to 2016. He's a founding member for China, Canada, Three Gorge River Reservoir Water Science Center, which is Southwest University. He's also visiting faculty there. He was just telling like 2 weeks ago, he delivered a lecture there. He received Tier 1 Canada Research Chair in Aquatic Invasive Species. In Canada, Tier 1 Research Chair is very prestigious, given to the top-notch individuals who do a lot of research. He received several awards. If I start reading all the list, like the whole hour will be for the list of awards and his recognitions. He trained several graduate and postdoctoral fellows. He published more than 250 research articles in reputed international journals. His publications were cited more than 24,000 times. And just to tell, his index, like I-10 index is 213, like out of more than 250, it's high. And he also received multi-million-dollar grants, several of them as a PI, more than 17 million. It's a like old number. I bet this number is way more than now. And as a co-PI, more than 30 million. So that shows like he is a reputed, worldwide known personality for invasive ecology. With that, I would like to invite to deliver the lecture this afternoon. Thanks, Hugh.
Before I begin, I'd just like to say that if you hang out long enough, you end up accumulating impressive statistics for how many grants you've had and how many papers you published. So it's simply a matter of how many heartbeats you've had in your life. At the same time, I feel horrible setting off, I think was a security concern because I work in China. I only know 4 words in Chinese. One is beer, one is a type of alcohol that I video, which I do not like drinking, and thank you and good morning. My job is really at University of Windsor, but we do have an alliance between the 2 universities, and I think that I'm the person that has exploited it the most. So here we are. What I would like to do today is describe progress in a very important environmental topic. When you think of the situation we are in, many environmental problems around the world, habitat loss is the one that I think is the worst. Climate change getting progressively worse. And invasive species, depending on what ecosystem, they can be extremely important. But I hope what I can convince you today is that we've actually made significant progress in stanching the importance of this one pathway that brought alien species into the Great Lakes. And as you know, many of them have been very, very disruptive. My co-author on this is Marco Hernandez. Marco was once a PhD student of mine. He's back working in my lab as a research associate. How do I go forward? Oh, no.
Here. Sorry.
Okay.
You can click on.
Okay. Try not to move it. Okay.
Yeah.
So living in the Great Lakes Basin, I think that most lay people, as certainly most people that work in an institute like Laurel, would be familiar with the importance of ballast water. There are a couple of images here. The top one is definitely a laker. The other one looks on the left looks like a laker as well, of a ship ships discharging ballast water. This water is usually picked up in one part of the world and is carried when a vessel does not have cargo, and it is discharged in another part of the world where the vessel is going to load cargo. We found that on average, ships would only do this about 5 or 6 times a year. So it's not an economically feasible strategy to be carrying ballast water when you could be carrying cargo. Same concept as taxi cabs going to and from an airport and having rides in both directions. So despite the fact the number of discharges per year by vessels really isn't that large, there's a minimum of 30 to 50,000 commercial vessels plying the oceans at any one time. So there's still an enormous volume of ballast water that's moving around the world. On the right, we're actually inspecting, I don't know, Dave, if you can recognize the people in the picture, but together with people at GLERL, we did a lot of experiments where we were looking at ships that were coming into the Great Lakes that officially should not have been a threat. But we found a pathway that would allow these vessels to still introduce species into the Great Lakes. So in order to examine that threat, which I'll talk about, we had to send people down into the ballast tanks. So Jim Carlton was a prof at Williams College, and he's considered the global guru for aquatic invasive species. Most of his work was on marine systems, but he also worked in freshwater systems, including on the Great Lakes. Here, he conducted a review of the history of ballast water, and ships, of course, used to be wooden vessels, and they used to carry solid ballast, mainly soil, sand, or rock, and it was cumbersome to put into a ship, and it was cumbersome to get out. So around 1880 to 1890, we saw a large shift as steels became, or as vessels became steel hulled. And once that happened, they switched over to liquid ballast. The first papers describing species moving around the world in ballast water were published just before 1900. And you can see that one study, I actually summarized it in 4 lines. They found an enormous array of different types of taxa that were being carried by ships. So we've known for a long, long period of time that species can be moved around in ballast water. There was a seminal report that was published for Environment Canada, which is a federal agency in Canada, in 1981. And they warned that from an examination of 55 ships that were coming into the Great Lakes, they examined the ballast water, and they said there's a lot of stuff contained in these vessels that could potentially cause a risk in the future. And unfortunately, at that time, even though the reports were published in 81, the government took no action. So as I mentioned, sampled 55 ships. Most of the vessels were from Europe, the US, or the Caribbean. Surprisingly, only a small number of them were carrying freshwater ballast, 3. 19 had brackish water, and 33 of the ships they studied had oceanic water. Now, looking at this, 49 of the 55 ships, they found living invertebrates in them. A total of 56 different invertebrate taxa were represented. A lot more phytoplankton species, and unfortunately, the phytoplankton really haven't been given the type of treatment that animals have. But you can see that there were a lot more species of algae that were coming in than of animals. Now, what I found truly interesting in this paper were the things that I've highlighted in blue. They reported that an animal called the zebra mussel, and they misspelled both the genus and the species name, Dreissenia polymorphus, was not found in any of their samples, but they said, based upon European literature, where it's found, we think it could survive if it was introduced to the Great Lakes. They recommended sampling ships coming into the Great Lakes more thoroughly to see what was coming in. And the 2 other important things, which together with Dave and Tom Johangen, was going to say Tom Nalepa, Tom Johangen, we conducted comprehensive sampling of vessels that carried only what was called residual water at the bottom of the tanks and sediment. And what they mentioned was that sediments were not sampled, but they thought that it should be followed up on because the sediments can contain a wide array of either cysts or in some cases living species. They also recognized that certain biological groups that were being carried in the ship ballast have asexual reproduction or so-called parthenogenetic reproduction. Many of those same species like Daphnia also are capable of producing cysts that can allow them to survive unfavorable conditions. So I think it's really tragic that this report, I think, gathered dust when if we had taken action immediately, we may not be where we are today. Turning to the Great Lakes, there were two species that I think drove a lot of attention among government officials. The first was the invasion of the Eurasian ruffe up in Lake Superior. Surprisingly, the species hasn't been able to spread very well because it's kind of landlocked in a cold lake. The other was the zebra mussel, and the ruffe was found in 1986. The zebra mussel was found in 1988 in Lake St. Clair, but Jim Carlton, once again, I don't know where he got the intuition or the lead, but he found that gas wells out in Lake Erie that are regularly checked for their condition by scuba divers, the divers had found unidentified animals clinging to the legs of the gas wells back in 1986. So we know the zebra mussel was introduced at least 2 years prior to its discovery in Lake St. Clair. So these two species, of course, particularly the zebra mussel, are now legendary in the Great Lakes community. There was a study published a couple of years ago by Sarah Bailey and colleagues, and they reviewed aquatic invasions of freshwater marine and estuarine habitats between 1965 and 2019. And this is a global study. And here they're just summarizing the importance of different pathways by which invaders are thought to have invaded these ecosystems throughout the world. And you can see that ballast water and hull fouling were almost exactly the same, and they're both very, very important. So what we were discovering in the Great Lakes was not dissimilar from what was occurring in other ecosystems around the world. Now, a favorite topic of mine is talking about rarity and what does rarity mean and how do we deal with it? Well, we really haven't dealt well with it up until the advent of molecular barcoding. And barcoding is fabulous because it allows you, using species-specific markers, it allows you to identify the presence of an organism at an abundance orders of magnitude lower than we could using traditional plankton nets and microscopy. So this is a study done by a postdoc in my lab at the time, Ivan Zahn, and it's one of my favorite studies. So in the upper left there, I'm simply showing that because of the higher sensitivity of eDNA, we can reduce the time period before we can detect a population in the environment. On the lower left, I highlight two ports. The first port is Victoria in British Columbia, Marine Port, and the one on the Great Lakes is Hamilton Harbor in Lake Ontario. And what my colleague did is he took water samples from both locations, broke it into two. So we have two replicates, Hamilton 1 and Hamilton 2 in the red and purple. And then the British Columbia marine samples are the green ones. And on the x-axis, we have the essentially sequence abundance. And the dotted line and the round circles show the reproducibility of your results. And if you have very large numbers of sequences, you get very dependable, very reliable results that can be reproduced 100% of the time. As you move across the graph, once you're down into tripletons, doubletons, or singletons, meaning there's only a single or 2 or 3 sequences present, then the reproducibility of the results becomes hit and miss. So most people would say that you should have a minimum of 10 in order to have reliable. In other words, if I accept these singletons, what I'm likely going to find is a huge number of species that are present. But most of those singletons are going to be false positives. And you have to root those false positives out. Otherwise, you end up with data that's not useful. So Ivan was one of the first ones that was showing this, and the sensitivity, the ability to reproduce your results is highly dependent upon how many sequences were present. Now, the other thing Ivan did is he took 2 marine species, the larvae of those marine species in yellow, and he was going to introduce them into a Lake Ontario sample. So we collected a plankton sample from Lake Ontario, and we're going to introduce these 2 species that have previously been barcoded. We know what their barcode is. They have no business being in Lake Ontario because they're from the West Coast in a marine environment. So if we detect them in our sample when we're analyzing our sequences, it's telling us that how low we can go and how many sequences or what percent biomass can we go down to and still have confidence that we can detect this species if it were a real invader, which it's not. So the yellow ones are larvae that are being introduced into the freshwater sample. And on the far left, we did a serial dilution of an individual larva. So instead of starting with 1, we went all the way down to 0.01. In other words, we're not putting in 0.01 of a larva. We're extracting the DNA and we're putting in 1/100th the amount of DNA from that larva into the sample. And the 3 reverse to 3 replicates. So you can see for both species, when we have 5 larvae that were introduced to the sample, we always were able to detect the presence of the species in the water. And then as we go down, the sea cucumber, we could actually get down to 0.1 of a larva and still be able to detect it in a sample that had tens of thousands of other organisms in it. So it shows very, very high sensitivity. On the right, we're taking freshwater species larvae and we're putting them into the marine sample and doing the same thing. We have 2 different dilution factors. That's why the graph is table's a little messed up. For the golden mussel, we went from 0.01 to 5 larvae. For the water lice on the far right, we went down to 0.001. And you can see that as you are increasing the dilution factor, your ability to discern or to find those that species in the sample goes down. But in the case, we were able to get hits down as low as 0.001 of a single larva. So this method is now very widely used throughout the world. And we used it on a lot of our studies. I know different labs, university and government labs throughout the Great Lakes Basin do this as well now. Now, because of the concerns about species invasions, the International Maritime Organization, which is a UN agency, in 2004, after a whole bunch of horse trading back and forth, countries like Greece said, we don't want strong regulations because we do a lot of shipping. We don't want our business affected. The US, to your credit, took the exact opposite tack. They said, we want extremely stringent limits on what can happen, okay? So they came up with a regulation called D-1. And D-1 says you must do open ocean ballast water exchange. So if I have water from a freshwater port like Rotterdam, as the ship comes across the ocean, it has to put salt water, it has to exchange the fresh water in the tanks for salt water. By doing that, we're going to purge most of the organisms that were in the tank are going to go into the ocean and die. we're going to pick up the oceanic water, which typically does not have a high density to start with, and we can safely dump that into the Great Lakes because those species are strictly capable of living in highly saline environments. So this was a policy that was first adopted on the Great Lakes and then in other locations around the world. So does it work? The vessels I'm referring to are the ones in blue at the top, the ballast on board. So these ships are coming over without cargo. It used to be back in the early 90s, a lot of them were Russian grain haulers. We weren't buying ladas, so they weren't bringing ladas to North America. They were coming over with water, and then they were bringing wheat back to feed their population. So unfortunately, this regulation, people thought that this would really dramatically reduce the number of invasions. I'll show you it did not. And the reason why we think it did not really work is because it only affected about 10% of ships. 90% of ships were coming in with cargo and were exempt. So Canada had a voluntary regulation for them in 1989. The US followed in 1993. And because all ships have to go through territorial US waters, every vessel coming into the Great Lakes would now be covered by the US rules as of 1993. Now, I'll show you that the invasions continued. And so we started looking at how else could these new species be getting in? They're clearly waterborne. A lot of them were waterborne plankton species that are not involved in any type of pet trade or anything like that. The only plausible mechanism that would allow them to get into the Great Lakes was ballast water. Now, you could argue, you could have time lags that make it difficult to try and identify when did it really come in. But if you want, I can talk about that during the discussion. I don't think it's that important. So we recognize this second category of ships, the no ballast on board vessels. They accounted for about 90% of the traffic that was coming into the Great Lakes, and they were unregulated. We also know from doing initial examination that they could carry up to 50,000 liters of water in their tanks, and they could have anything from no sediment to huge accumulations of sediment. Then, while they're operating on the Great Lakes, perhaps they're dropping off steel rolls, first in Detroit, and then Chicago or Indiana. Each time they drop off steel rolls, the vessel now is going to float higher. They have to maintain the same trim, so they fill the tanks with Great Lakes water. That now mixes the Great Lakes water with whatever water was in the bottom of the tanks. And then eventually, to maximize their efficiency, they would end up usually on Lake Superior, either Thunder Bay or Duluth. They empty the tanks because they're now going to take wheat out of the Great Lakes. So we thought that that was a pathway that would allow the invasions to continue. I should mention that a whole group of people in my lab worked on a variety of these projects, examining this second pathway. And my two colleagues, I didn't realize Dave was going to be here today. I'm glad I put the picture in. We ended up with, I think at the time it was the largest grant given by the Great Lakes Protection Fund. And I think they actually got a lot of value out of the work that we did because the number of studies in this grant was enormous. And so Tom and Dave did a lot of work on that. Now, the data I'll show first is what I'm going to call opportunistic sampling. We had hired a retired ship captain to make contact with the seaway authorities and with shippers because you needed permission of both in order to be able to collect samples from them. Once that was done, we would either move to US or Canadian ports and we would sample the vessels when they were in dock. And here what we're looking at on the left is the invertebrate abundance in the ballast water. I'm later going to refer to the abundance as propagule pressure. So here we're looking at the abundance of invertebrates before the regulations came in blue, excuse me, and after the regulations came in red. And you can see that the abundance went dramatically lower after this IMO D-2 was brought into place. On the right, we're looking at species richness. In invasion ecology, we call that colonization pressure. I'm going to talk about that very soon as well. The difference here wasn't significant, but if you look at the air bars on the ships for the pre-period versus the post-period, in the post-period, we saw that not only did the mean number of species coming in that posed a risk decline, but the variance among the ships declined as well. So as we'll see in the future, I think both of these results were indicative that the likelihood of new invasions would be much lower. The other type of studies that we did were experimental. And we wanted to assess the risk of European vessels, European water coming into the Great Lakes and bringing species over. But it was hard lining up traffic shippers that would allow us to work in Europe. So what we did is we lined up North American ships that were operating on the Great Lakes and were going to go to Europe. And we had them fill their tanks with fresh water. We would sample the water before the ships left for Europe. The students would ride the vessels across. They had many free trips to Europe. They would ride across, and we have our control tanks, which did not experience ballast water exchange on the ocean. And we had our experimental ones, which did. And you can see we had roughly the same number of species starting out on the left in the two different treatments. And then on the right, only the tanks that had experienced the ballast water exchange on the ocean had a significant decline in the number of species present. So this combination of observational studies, opportunistic observational studies, and experimental studies convinced us that salt water could be an effective means of guarding the Great Lakes from future invasions. Now, enough time had transpired that after the second policy came into place, the US and Canadian governments in 2006 and 2008 said, if you're one of those 90% of ships that only has residual water at the bottom, you too must put salt water in when you're coming over. We don't care what you do with it. You can spit it right back out, or you can bring it in and dump it. It's not perceived to be risky. So those rules were using 2007 as our cutoff here, but Canada started in 2006 and the US harmonized to that in 2008. So we have 3 time windows. Each one is 13 years in length. And we're looking at the number of new reported invasions associated specifically with ballast water. You can see for the green period with no regulation, it was 16. For the second period in yellow, it was 15. And for the third period, it dropped down to 2. The total number of invasions is a little bit different and a little bit higher because not all of the species coming into the Great Lakes are associated with ballast water. So the total number for those same periods were 19, 26, and 4. And the number of new invasions each year associated with ballast water for the initial period, 1.46. It actually increased a bit to 2.0 for the intermediate period and 0.31 for the final period between 2007 and 2019. So overall, looking at the overall reduction, it was 85%. Looking at the reduction in ballast-mediated invasions, it was 87%. Now, when we first sent this to the journal, the reviewers liked it, but they said, convince us that some other mechanism that can't account for the pattern. So I'm going to show you the ones that they asked us to deal with. The first one is reduce ship traffic. And you can see for the different time intervals there was a decline between the first period and the second period, and between the second period and the third period. But the difference between the second and third is not significant, and it's nowhere near the scale that you would require in order to get an 87% reduction in ballast invasions. So we were able to reject that hypothesis. The second hypothesis is one that I'm interested in. It's called the depletion hypothesis. About 65% of the invaders that have come into the Great Lakes since the modern seaway opened in 1959 are believed to have entered via ballast water from Europe, okay? So if we're getting all of these European species shown in the green circle, European species that are being carried over by ships and colonizing the Great Lakes in red, eventually you have to get to the point where any species from Europe that could colonize has colonized. And that means that you have a negative relationship between the number of potential new invaders and time, okay? If you look at the available data for invasion patterns around the world, I want you to focus on Europe, which is the black line. And I'd like you to look at the bar on the far right, or the graph on the far right, the fishes, and the two on the bottom on the right, the mollusks and the crustaceans. They all are basically the same though. Upward curves over time. So Europe is becoming progressively more invaded with new species. A few of them are from North America, but many of them are from Europe, other parts of Europe or Asia. So we think we can reject this hypothesis of depletion as well, because Europe has more and more species, many of which have an invasion history, that are available to come over to the Great Lakes. The third one is reduced search effort. And particularly for the latter period, we think that you can outright reject this hypothesis. Concern about invasive species really exploded beginning, I would say, as far back as 2000. I remember attending public fora where people were really harassing government officials saying, do something. Governments on both sides of the border responded. EPA monitoring study, US Fish and Wildlife, Department of Fisheries and Oceans was heavily, and Environment Canada were heavily criticized by our independent auditor of government. And after that, in 2002, they started ramping up programs. They gave me a research chair. They ramped up programs on aquatic invasive species in the Great Lakes in particular. And our CASIN network, where we had people all across the country, but dozens of people working, trying to find and examine invasive species. So if anything, search effort for the latter time period was much higher than it was for the earlier ones, which means that the likelihood of us finding the species would be much higher as well. So we can reject that hypothesis. Now, the review paper that I showed you a few minutes ago about the importance of ballast water and hull fouling, they also had this graph, which is quite interesting. Very clearly, we've seen a large decline in the number of invasions in the Great Lakes. And here they're looking at all these ecosystems throughout the world, and they're seeing essentially the same thing happen. I'm not sure what the reason for that is. It could be that ship husbandry is much better in terms of making sure that you don't have hull fouling organisms on the ship. At the same time, that global ships started doing this open ocean ballast water exchange around 2004. Now, we come back to these two concepts. These are probably the two leading concepts for predicting invasive species. Propagule pressure, which is the number of individuals introduced. We can break it down to two components: the number introduced per event and the number of events. The second one is called colonization pressure or species richness, okay? And I'm going to show you a new regulation that will come into place in September 2024 in a minute. The IMO did not just rest on ballast water exchange, because they realized there are a lot of cases where ballast water exchange does not work. So what they're going to do instead is they're going to regulate the abundance of live organisms that you can discharge. And that's going to follow under the second definition there, community propagule pressure. Community propagule pressure is the total abundance per unit volume of organisms that are being discharged in ballast water. The top one is similar to the one that I had in the last one. When we think of propagule pressure, we usually think of the propagule pressure associated with an individual species. It doesn't do me any good trying to colonize if I have 8 bugs trying to colonize the Great Lakes. It doesn't do me any good if there's 12 bugs of another species that are also trying to colonize, okay? What I want to know is how many individuals of a species are present, because that can be very important when you're trying to find a mate in a new environment. So the individual propagule pressure is the propagule pressure associated with a single species. Community propagule pressures associated with all of the species in a sample. And colonization pressure is simply a number of species, once again. Now, for individual propagule pressure, there's hundreds, maybe thousands of papers that have been published on this. Very clear evidence supporting the importance of propagule pressure. And you can see that there are 4 different types of curves that could potentially explain the risk as a function of the number of individuals released. There was a paper published in 2013 by some pretty smart people. And they argued that in the absence of density dependence, what we expect is a hyperbolic relationship, the one that's shown there in red. If you do have density dependence, you could end up with the one in green. So I'm going to end up using this hyperbolic function in a few minutes. There's a lot of empirical data to support the importance of individual propagule pressure. First study is from mesocosms that were set up out in Lake Ontario. The second one is from just Daphnia cultures. It appears here that it's either a hyperbolic function or a linear function that would explain risk. There's dozens of other examples I could show you, but I'm not going to. If we turn to colonization pressure, the term wasn't actually coined until 2009. Prior to that, people may have referred to it, but they called it species richness. And what we're showing here is the expected relationship between the number of species that will establish on the y-axis and the number that were introduced on the x-axis. And just from random modeling alone, the gray dots, there's a positive relationship that's expected there, an asymptotic relationship. And if you look at data for birds that were introduced to islands, you can see it follows that pattern very, very closely. So colonization pressure is also important. Think of it as buying lottery tickets. I don't buy lottery tickets, but if I did, I would prefer to have 10 than 1, okay? The likelihood in this case that if I introduce 10 species, 9 of them may not like the environment, or they may not have the right sex ratio. They all die, but the 10th one survives. If there's only a single species being released, the probability of that invasion succeeding is much lower. Now, the reason why the IMO was skeptical about ballast water exchange is what I'll show you in the next 2 slides. The first one is part of our occasion studies where students boarded vessels in Asia, rowed them to British Columbia, and every day they would collect ballast water samples from the tanks. And what they're quantifying here is both the community propagule pressure and the colonization pressure. We always expect this type, there should always be an asymptotic function, okay? So day 1, the blue curve, you can see lots of species, high abundance of organisms. By day 6, I think this water came from a Chinese port and it was probably nasty water. So once it was put in the tank, most of the organisms started dying off. So by day 6, there's hardly anything living in the tank. Then on day 15, halfway across the ocean, they did ballast water exchange. And they end up picking up new species, some of which survived to when they landed in North America. So this would be a concern because we want to reduce risk when what we might be doing here is increasing risk by doing open ocean ballast exchange, especially for one group of organisms called the dinoflagellates. The other data comes from the United States. Here, Whitman Miller and Greg Ruiz and their colleagues, they tracked every vessel that was coming into ports on the East Coast, the West Coast, and the Gulf Coast. So for the transoceanic vessels on the left side, you can see the vast majority of them have conducted the requisite ballast exchange while they're on the ocean. A small percent were exempted, the ones in black, because of really nasty weather conditions, which would endanger the ship. So they didn't do ballast water exchange. Now we go to the right side. And particularly if you look at the Gulf Coast, because these vessels are only moving up and down the US coast, the IMO wrote into the regulation that you do not have to diverge out into open ocean, do exchange, and then come in. It would be a colossal waste of money and fuel. So a huge percentage of the vessels moving along the coastline of the United States have done neither ballast water exchange or they've only done coastal exchange, which means you could still be seeding a port maybe 500 or 1,000 kilometers away with organisms that you picked up at the first location. So for these two reasons, people realized that ballast water exchange, while it worked for the Great Lakes, it did not work or does not work very well for the marine environment. And they said, we must come up with a new alternative. The new alternative, which was also agreed to in 2004, they put it out to the global community for ratification. You have to have a certain percentage of countries and a certain volume of shipping that are represented that approve of it. The numbers were 30 and 35%. So about 35% of countries had to approve before this thing would be officially ratified as a UN document and come into law. And then that happened in September 2017. They said we have to give ships time to put water treatment systems on board. And so they said, we'll give them until September 24 to have these systems in place. They're called performance standards that the ship's treatment systems must meet. The treatment systems have to be independently verified that they work, and then they can be sold and put on board the ship. Once they're on board the ship, no one's checking to make sure that there's compliance. They essentially operate on a red light, green light system. It's either working or it's not. But all of the systems in use must be verified that they work. So the organisms we're most interested in are the so-called macroplankton. These are the zooplankton. And the standard for them was less than 10 viable organisms per cubic meter. Now the ship could have thousands of cubic meters. So a legal discharge could still have lots of species in it at high abundance. But if you consider what occurs in a lake during the summer, freshwater organisms in a lake, I estimate that you would have about 100 individuals per liter that would be in that size category. 100,000 per liter is 100,000 per cubic meter. They have to get it down to less than 10. So they have to have a 10 to the 4 reduction in plankton abundance using these water treatment systems. 3 bacterial indicators and 1 for phytoplankton as well. Now, our concern, we get paid to just sit back in my chair and think about stupid stuff. I said, wait a sec, they're only talking about this idea of community propagule pressure. It has no basis in fact. There's no scientific evidence to support a community propagule pressure, because that's not how species invade. They invade individually, okay? So first I was concerned with they're setting this standard based on community propagule pressure. And secondly, the other component of invasion that I showed you, colonization pressure, isn't being considered at all. So here I have 6 different communities, all of which, now we're using acceptable to be equal to 10. The regulation says it has to be less than 10, but okay, just to let you know. So we could either have one species present at 10 individuals per cubic meter, or we could have 100 individuals present at 0.1 per cubic meter. Is there a difference in the risk profiles for each of these different communities? So we're going to show you some studies that we did to try and assess that. Again, we're going to use the 4 different types of individual propagule pressure risk curves: linear, exponential, logistic, and hyperbolic. Now, the standard, as I'll show you in the next slide, the standard is set at 10. You can see my x-axis here runs out to 50 or to 5,000. So if we look at it across a very broad spectrum of community propagule pressure, you can see that colonization pressure is important, and the highest risk is also always associated with the most species that are being introduced. And over this large community propagule pressure, it also becomes important, and there's a significant interaction between them. But that's not what's relevant. What's relevant is looking on either side of the 10 that was agreed upon. How did they agree upon 10? Well, unfortunately, I wasn't there, but I know what happened. You have countries that have different concerns. I'm mainly worried about shipping jobs. I'm mainly worried about the environment. And they ended up having to come together, and they reached this magical number of 10. So for the first 3 types of curves, ignore the hyperbolic one. Notice the increase in risk as a function of community propagule pressure for the first 3. It's virtually non-existent on either side of the 10 limit. It could be 1, it could be 25. I have almost the exact same risk associated with that. The lower the limit we set, the harder it is for technology to meet that limit, okay? So if the curves that describe risk are any of those first 3 on the left and bottom, then the number that they chose is not supported. If we consider the 4th one, it's a hyperbolic function. And what we're doing is we're starting out with a high abundance. How am I going to do this? We're starting out with a high abundance, and I'm making them treat the water so the abundance starts dropping. And as it drops at an if you took, remember your bad calculus when you're a high school student, the rate at which the drop is occurring is increasing as you drop it per every unit. So in this case, the standard should be as close to 0 as possible rather than at 10, okay? So from this, we once again see that the major factor that contributes to risk is colonization pressure, not community propagule pressure, okay? The one that's being regulated. Now, so once again, what I just mentioned, we're starting out here with a large number of species, but we're only regulating this. And we say, you must get down to here. And by doing that, they inadvertently also bring down the colonization pressure, okay? We looked at all of the what do you call them? Reports of every IMO meeting to see if they ever talked about colonization pressure. They never did. We looked to see if they ever talked about species richness. They didn't. The only time we ever saw a mention of the potential importance of colonization pressure, we were reviewing the United States government conducted their own review of risk associated with these discharges. And as part of their review, they sent the material out to a whole bunch of experts in the field. I wasn't one of them. I don't know if Dave got it. But when we went through that, we were able to find one of the reviewers said, I'm concerned that there's no mention of the importance of the number of species that are being released. That was the only mention we could ever find about it. But the good news is, by reducing the community propagule pressure, we also end up bringing down the colonization pressure. And I'll show you the way that that works. These are ballast water rank abundance distributions. So on the x-axis, we have the species rank from the most abundant on the left to the least abundant on the right, and the abundance of the organisms is on the y-axis. So 25 different samples, you can see that a few of the samples had pretty high abundances of individual species, but in most cases, once you're past about 5 species, there's not very many of them in the tank. What we think is happening when we're doing treatment, assuming that all species are equally affected, what we end up doing is we reduce the abundance of everybody by at least 10 to the 4. And when you do that, notice the Y scale has now changed. What we end up doing is we drop off the species that were present in those samples at the lowest abundances, okay? Will it work? There are only 2 studies that have been published. Ships have been putting these ballast water treatment systems on board their vessels since 2017. There are only 2 studies that provided data that we were able to test this idea with. And before I go further, I'm going to go back to that hyperbolic function, the one in the upper right. And what we're going to do, we're going to extract colonization pressure data and community propagule pressure from each study, and we're going to map them on those graphs to see where they are, the risk. So this is not good news. In the port of Shanghai, they were sampling. 9 ships were compliant, 8 were not compliant. For the 8 that were not compliant, we show the colonization pressure, CP, and the community propagule pressure, CPP, as well as the what we believe is the likely probability of an invasion occurring. The same thing for Canadian ports, sampled by Sarah Bailey, almost the exact same failure rate, 14 failed, 14 passed, 15 failed. And once again, we get a variety of risks associated with these vessels. So for the 2 studies that have been conducted, about 50% of the vessels are not compliant with their discharges. And remember, those numbers for CPP, they have to be less than 10 in order to be compliant. And you can see some of them are out by 2 or 3 orders of magnitude. That being the case, what should we do? Well, because we have a gateway to the Great Lakes, we once proposed to Transport Canada that why not still require ballast water exchange in addition to doing ballast water treatment? If the ballast water treatment fails, currently, we have no backup. If we also do ballast water exchange, because we have this unique environment where any freshwater species could be purged on the ocean, we think that we could still get protection. So if you just look at the zooplankton data, that's number of organisms, the abundance, in non-exchanged, non-treated water on the right, the black bar, we have a log scale for the abundance. So the second one is a ship that did just ballast water exchange. The third one is where we added chlorine to the ballast water. And the last one, we did both treatment and ballast water exchange. And you can see that the results there are putting us right around the IMO D-2 limit. So if we're concerned about protecting the Great Lakes from future invasions, it doesn't cost the ships any money to also do an exchange while they're coming across. What happens if the system breaks down? It's largely the same thing. We did more modeling of the risks. And what I'll just comment here are the 4 right bars. The partial ballast water exchange is the bar in the middle of the B. The partial ballast water exchange, ballast water management system, that's water treatment. That's the B. The one beside it, the C, is ballast water treatment plus ballast water exchange. Fully functioning ballast water management system is the second bar from the right. So we almost have the same results in terms of risk. If a ship is only doing partial ballast water treatment, that could be because it has a high sediment load, too many particulates, whatever. So if they were also combining that with ballast water exchange coming across, we think the risk could be quite low. And the final one, this is specifically for the Great Lakes. What we did is, from the measurement of all of the abundances of organisms in the different ships, we classified the ships as either being 3 categories: high risk, top 10%, low risk, where the low density were the lowest 10%, and the 80% is in the middle that we're not looking at. But here, if you look at for both high density discharges of organisms and low density discharges, if there's no treatment, the risk is highest. If you do partial treatment, you get a partial reduction, which means even if the system isn't working completely, we think they should still be running it. And the final one, if they're doing full treatment, you get the best benefit. Last slide. I made predictions years ago that I thought that the ballast water problem in the Great Lakes was really going to be diminished once first IMO D-1 came in and then IMO D-2. Even if it's not perfect, I think the risk is much lower than it used to be. And if that's true, and I think the available data suggests it is true, then you can argue, what do we do now? I would say let's focus on other pathways that can bring species into the Great Lakes. We know in both the United States and Canada, there are a lot of species being sold freely either in pet stores, aquarium stores, or on the internet, where you can buy and have these things shipped to you. And some of them could be potentially problematic for the Great Lakes. And so if I had to focus on anything in the future, that's the thing I would look at next. And I'll stop there.
Thank you so much, Hugh. Good actually at the time, but we do have 1 or 2 questions. So please go ahead. Anybody want to ask?
Hey.
So, yeah, you've done a great job covering tips coming in from the outside. The big issue now, the big issue now is whether or not to make Lakers include treatment, because they're talking about the internal movement within the Great Lakes. And I'm just curious where you stand on this I'll preface my remarks by saying my thought processes go back and forth on this, but one thing I say is, okay, Lakers have been operating on the Great Lakes since, I don't know, time immemorial, at least several, over 100 years.
Yep.
So the system is pretty well stirred. However, of course, as new species came in, they had the opportunity to be moved around by Lakers. Now that we have, since about 2008 or so, very few new species that can be picked up in ballast water, is it necessary, especially given the difficulties of putting that type of a treatment system that will work on Lakers? And I was just wondering what your thought processes are.
I think they absolutely should be regulated, no question. And the reason why I believe that, and we actually need data for this, and it would be easy to assemble. You simply look at the total number of non-native species established in each of the Great Lakes. And we're mainly worried about ships that are moving up the lakes, okay? They're not, it's rare that they would be carrying ballast water and coming down. They're carrying cargo. So what I would like to know is how many species are present in each of the Great Lakes and the identity of those species, and how many of them in Lake Ontario and Lake Erie are not present in Lake Michigan, Lake Huron, Lake Superior. And with that information, you, in my opinion, you would then have potentially a very strong argument saying, look, I forget the number. We did a calculation years ago, how much water is being moved by Lakers versus ocean boats. And it's something like what, 95%? 95% is by Lakers. So ocean vessels could still introduce things, but they're being managed. So I would focus on the ones. If in fact there are lots of species that haven't made the journey north yet, I would look to regulate them. One of the problems, as you know, with the Great Lakes vessels is they're operating almost exclusively on the Great Lakes, some of them exclusively on the Great Lakes. Many of the ballast water treatment systems use chlorine, and they strip the chlorine from seawater. So if they don't have seawater, then you're going to have an artificial source of chlorine on board the ship to replace that, which they would normally be getting from the ocean water.
Don't forget also Lakers, just as far as I know, all of them do not have coated tanks, so stuff with chlorine and dissolve. These are ongoing issues. I know I'm sort of not surprised, but I think it's the new issue that we haven't really fully figured out how to address yet for the Great Lakes.
I mean, I should actually put an undergrad on that. That's a very simple project to do. And from, you do? Yeah.
We need more of the Canadian data added to be conclusive and to push more of it to a more refined geographic scale, but lake to lake, we've got that data.
And, you know, if you wanted to push it further, you could say, okay, we have 8 species in Lake Erie that are not in Lake Michigan, Huron, or Superior. You could then say, what are the potential modes by which that species could be moved to other lakes? And if it's highly likely to be moved by recreational boaters, then you may say, you know, why penalize the shippers if it's going to get there anyway by some other mechanism? But when you're bringing the volumes of water in those Laker vessels up to the upper Great Lakes, for many of those species, probably all of the planktonic ones, that's how they're going to move. I know the Lakers, you know, their argument going back 15, 20 years was, we don't bring species into the Great Lakes. And I go, yeah, you're absolutely right. But it doesn't mean you're not moving them around. And that's a part of the problem too. If I live in Lake Superior, on Lake Superior, and I don't have some of these species in Lake Superior now, I view that as a new, completely new invasion, sending it up to my lake.
The other thing that when people are discussing this issue, they don't think about is, okay, on one hand, you can say, well, they're going to be moved, you know, if not by lakers, by recreational boaters. So, you know, just what's the big deal? And I remember reading, I don't know if it was a study, we call it just a story, that if when the zebra mussel was spreading around, and they were saying it takes a water, like a power plant, which uses cold water for cooling, if they have to spend $250,000 a year because the zebra mussel's covering their cooling things, then if you can delay the invasion of zebra mussels to that location by 10 years, look at how much money you're saving. So the same thing, in a sense, could be applied to moving stuff from the lower lakes to Lake Superior. And it just depends on what the impact is likely to be.
So with zebra mussels, if you recall, when they invaded Lake Mead in Nevada, California, David Lodge had published, it's like the guy's a soothsayer, you know, he's his guru. He published a paper the same month in Ecological Applications saying zebra mussels are at highest risk of spreading in the Western United States to Lake Mead. And it's like he paid divers to go down and check. And they didn't find the zebra mussel, they found the quagga mussel. So when you have a biofouling species, like either one of those, the risk is that even a local boater, by getting that on their trailer or on the boat and then moving up to Lake Superior for a vacation, it is possible that they could spread them. It's far less likely that species like the fishhook water flea or the spiny water flea, they don't have that adherent capacity other than maybe sticking the fishing line. What they're going to do is they're going to have this hopscotch pattern of dispersal, and that's exactly what they've done. They've slowly radiated out, but you never get the long distance dispersal event that you get with the zebra mussel. So I agree with you 100%. Time is money. And for any of those industries, we tend to only hear the one side of the argument. And I know that the Great Lakes shipping community is very concerned about regulations, but I don't know if the regulators hear from the other side, the impacted side. We have power plants all across it, municipal water intakes. We have all kinds of users of water that are negatively affected by the spread of an invader. All set? Good.
Thanks, Hugh, for the great talk. Thanks, everybody.